Hello, and welcome to Tech to Tech presented by KYZEN, where we will explore common cleaning questions and answers. Let's get started. I would like to introduce KYZEN's own Rich Burke.
Thanks, William. I want to welcome you all to today's Tech to Tech session. This is going to be a two-part session series focusing around rinsing in the rinsing process. Today, we'll focus on the fundamentals for a successful rinse process and high-level overview. The second session will take place October 17th, and that will be more case study review and discussions. So with that, let's look at what makes up critical components, let's say, to a successful rinse process. And there really are three key pillars or building blocks. And I'll touch upon each of these. First being a cleaning agent itself, the engineered cleaning agent and what it's intended to do. Secondly, equipment, both batch and inline, and the process in terms of the equipment aspect of it. And then lastly, but not least, is the water source itself and the purification strategies that one would utilize. Before I jump into those three pillars, if you will, let's talk a little bit about why rinsing is critical. And more specifically, what are we trying to rinse off in assembly, right? So we know that we use a wash solution to remove the flux residues in the cleaning process itself. So in essence, that's what we're striving to rinse off in assembly. And that wash solution is made up of cleaning agent, obviously, but it's also going to have the solubilized contamination, the rosins, the resins, the flux activators, and so on, and obviously water. So in essence, that's what it is we're striving to rinse off our electronics assemblies. If we do not rinse those off, what are those risks? What may happen? Well, it depends on what the residue is, right? So in the case of an ionic residue, we can leads to dendritic growth or corrosion potential. If the component is an organic residue that's left behind, that can be problematic when it comes to bonding. That could be bonding of a conformal coating material, bonding of labels or part marking issues that may arise. The wash solution itself is designed to get into tight spaces, right? And so if we're unable to rinse that material out, we can see over time weeping of the wash solution under low standard devices, vented packages, or connectors. And then lastly, we can see cosmetic defects. We've all seen water spots on glassware or our vehicles after we do a car wash. So it's the same thing. Cosmetic defects can be, again, an area of concern, and poor rinsing can lead to cosmetic defects, including water spotting. So the engineered solvent, or engineered cleaning agent, I should say, these are complex formulations. They're designed to do a lot of different things. I'm not going to get into too much detail on the cleaning agent itself in this session. My colleague will touch upon this a little bit more in part 2 of the session. But what is really important is, let's think for a minute about what a cleaning agent is aimed to do. All right. First and foremost, we want that cleaning agent to be successful at removing the residue, the flux and the paste residue. The material also has to have excellent material compatibility characteristics. We want a material that is foam resistant. We don't want foaming in our wash tank, and we don't want foaming in our rinse tank. So foam resistant formulations. We want our materials, our bath, to last long, have a large loading effect, if you will. We want our materials to be environmentally and human friendly, so green cleaning agents. And last but not least, is we need a material that is designed to rinse well. So it is very important. And again, as we're formulating these materials, all of these aspects are considered. So again, for this purpose of this discussion, the formulation of a cleaning agent does have an impact on its ability to be rinsed. When we're doing studies and trying to determine our materials to be utilized, we want to, when we're talking about rinsing, this is one example of a test that can be utilized to gauge the rinsability, let's say, of a cleaning agent. In this case, what we're using is a glass slide. The glass slide is first cleaned. The slide then is submerged into the cleaning material for 30 seconds, dried for 1 hour, and then rinsed off with DI water. The slide is then left to dry. And then what we're trying to do is measure the surface energy of that slide. And we're using Dyne inks or Dyne pens to do that. And what we're looking for is, as you can see the slide on the left, we're seeing that Dyne ink of 72 wet out to the surface. That's indicating to us that that particular material has very good rinsability characteristics. Conversely, the slide on the right, we see it peeling back. So it's telling us it's below 72 Dyne, and that is indicative of a material that is less likely or more challenging to rinse off. It doesn't mean it won't work. It doesn't mean it can't be rinsed. It just means that it's a little bit going to be a little bit more challenging for the equipment sets to do the rinsing effect, if you will. The table on the bottom is just indicating some of these values, some of these levels, looking at different cleaning agents. I'm not going to get into too much detail on this. Again, in the second session, we'll jump to more of the analytics, if you will, or the case studies. But it does show you that different cleaning agents have different abilities to be rinsed. The fact that one is alkaline and one is pH neutral, that's not necessarily what's critical. It's more about what is the formulation that drives the ability for that material to be rinsed or have a little bit of a challenge when it comes to rinsing. So let's talk a little bit about equipment for a minute. So let's start with an inline cleaning system. An inline cleaning system, as we know, is made up of different sections. It starts with a wash section, ends with a dry section. And in between that, there are different modules that make up the rinse. In essence, in most cases, we would see a chemical isolation section, and that's designed to minimize the drag out or carryover of a wash solution into the main rinse section. The main rinse or recirculating rinse, and then a final rinse, which is where the highest purity water would come into the system. What you generally would see is a final rinse to rinse cascade system where the rinse water is flowing back to some kind of a purification system. In this case, is being shown with a DI water system. The chemical isolation section itself can be either fed from the main rinse as a power cascade system, or more often would be fed from either tap or RO water. Again, this is a gross rinse module designed more for isolating the chemistry than it is for, let's say, final or fine rinsing. And then typically that water would flow to drain. But there are different ways the system can be configured. When we talk about a batch system, it's just done differently. And in a batch system, you've got a single tank system. And so what it's trying to do is actually do a repeat rinse cycle or rinse in repeating cycles. And in this example, it's showing a rinse of 30 seconds. And then it's going to look towards either the resistance value, resistivity of the water solution, or number of cycles. One of these two conditions has to be satisfied before the rinse concludes. Otherwise, it will continue to run until one of these two conditions is realized. So if it never gets to 500 k ohm, but it's 6 cycles, it would end. Or if after the third cycle it gets to above 500 k ohm, it would end the rinse and move on to dry. So just a different way of accomplishing a successful rinse process, batch to inline or inline to batch. The other thing when we talk about equipment, which is very important, is to look at the configurations themselves. We really want the rinse to match as well as possible to the wash section. We do an effective job of getting the materials into places. We want to make sure we get the rinse has the capacity to remove those same materials back out of the system. So you'll see different nozzle designs and configurations, but what's important is to try to match the spray and nozzle configuration from the wash to the rinse as best one can. We always want to make sure that the final rinse is fed from the highest quality water. Again, that would very often be a DI or an RO system. I'll talk about that here in the next couple slides. Inspection of our systems is very important. Oftentimes gets overlooked. but we can see clogged nozzles or clogged manifolds. So it's important for us to do inspection of our systems. Obviously, if we have clogged nozzles, we're not going to get good cleaning or rinsing for that matter, right? So we want to make sure we're inspecting them. We should be having something on our systems that are monitoring the process. Very typically, that would be a pressure gauge or pressure sensor. In some cases, a flow meter as well. In a perfect world, you would see both. And the reason I say that is, we could have a clogged nozzle, as we show here in this lower picture. Um, and if we just had a pressure gauge, we would see the pressure go up, right? The back pressures, we're getting an indicator of the back pressure, but we're getting no rinsing. And if we had a flow meter, we may be able to detect the flow change. So now we're getting a truer picture of what's going on in that system. So in a perfect world, I would say both pressure and flow would be monitored. The next thing that's important is to separate the final rinse to the supply line fill system. And why that's important, think about when your wash tank calls for makeup water. When that happens, that's an open, low pressure pipe, right? So the water is flowing freely to the wash tank. That's going to then potentially steal the water from the final rinse. So oftentimes when we have a system that's not separated, that wash tank fills, if you were to look at your pressure gauges or flow going to the final rinse, we would see that drop off dramatically. At that point in time, those assemblies in that final rinse section would be questionable in terms of their ability to be rinsed. Let's talk about water for a second. So the water that's coming to our systems can have different things. We can have organics, we can have particulates, we can have minerals and inorganic material. So we want to purify that water. We don't want to be just rinsing in our final rinse with tap water, for example. So we want to purify water system. And very often that's either going to be reverse osmosis, RO systems with mixed beds for polishing, or a DI water system. Here we can see two examples of what I'm talking about, right? So on the left, an example of an industrial RO system where we would have a multi-stage pump, high pressure pump that forces the water through RO membranes. And on the discharge side of the RO membrane, we get a good quality water that can go back to our final rinse system. And again, very often after it comes out of the RO system, the water would go pass through a mixed bed for polishing purposes. So the end result would be 18 megohm water coming out of that system in many cases. The other approach would be to use DI water columns. And that's what we're looking at here in the image and the diagram to the right. And that's typically going to be made up of various tanks. First would be carbon resin. So the carbon is used to remove organic contaminants, cation, anion, and mixed beds to remove our positive, negative ions and to polish the water. And in both cases, we would typically have something to monitor the quality of the water, resistivity meter, either on one of these two systems or on the inline or batch cleaning system to monitor that for us. So in summary, right, there are really three important considerations. We have our cleaning agents themselves and the formulations. We want them to be designed in a way to be successfully, easily rinsed, both fresh, but also the loaded bath. So keep that in mind when we're making our selections of cleaning agents. Equipment, like I say, there's different configurations. We want to make sure we're matching the rinse as closely as we can to the wash section and doing our maintenance and inspection on those systems. And then lastly, we want to make sure we have a water purification strategy and a supply to achieve that strategy. Wrap up with a few frequently asked questions. The first one is DI water quality of 18 megohm required. Well, you've heard me mention 18 megohm, I think, a couple different times. It's not required. It's typically going to be what is realized when we come out of mixed bed systems. IPC spec does call for or suggest 1 to 5 megohm water quality at the point of the machine, right? So no, you don't need 18 megohm. It's very often going to be generated. It's not going to hurt us to have 18 megohm, and it's going to degrade over time. But again, IPC spec says 1 to 5 megohm. In the chemical isolation section, what is the difference between dry and wet isolation? It's a great question. So in a dry isolation system, it's using air knives to mechanically squeegee, let's say, of the water off of the assembly. The thing to keep in mind when you do that, if we have an assembly come in, we squeegee that water off, it then goes into the rinse section. The assembly is carrying forward not a lot of water, obviously, but what it is carrying forward to the rinse is of the concentration of the wash tank. So it can degrade the rinse over time quicker than a wet isolation. Second part to that is you can, in some cases, actually dry the some components or some areas of an assembly, and in some cases that can make the rinsing much more challenged if we pre-dry per se before it gets into the rinse section, the main rinse. A wet isolation is a combination, so it has a combination of air knives for mechanical squeegeeing effect, but what makes it very different is it uses a low flow of water to rinse and secondly dilute. So in that case, again, very little fluid flows back into the rinse tank, but what's quite different there is the concentration of the fluid that would be on that assembly is greatly reduced over that of a dry isolation system. So the preferred method would be a wet isolation when possible. Last question, when it comes to rinse temperature, what should be used? Again, IPC does talk about this again in the spec, and it says higher the better, or highest possible, without degradation of components and assemblies. And that would be true. I would say keep in mind too that when we're using DI systems for closed loop, the DI systems degrade over time as we get into an excessive temperature range. So we want to keep that in mind. But in principle, I would say be in and around the wash temperature range. It would be in most cases ideal. Think about we know that higher temperature helps from a rinse standpoint, just as it does in a wash standpoint. Just think about your dishes at home before you send them into the dishwasher. If you use cold water versus hot water, which is going to solubilize or rinse away the material before it goes in the dishwasher? Obviously, the higher temperature. So just keep that in mind. So with that, I want to thank you for joining and tuning in today's session. Hopefully it was informative and helpful. Again, as a reminder, do tune into the second session that will take place, as I say, at October 17th. So with that, thank you again, and William, over to you.
Thanks, Rich. Thank you guys for watching this Tech-to-Tech session. If you would like to discuss this topic further or have any questions not answered in the session, please contact your local KYZEN regional manager or send an email to tech@KYZEN.com, and we will have someone follow up with you as soon as possible. And if you like this video, be sure to follow us on our social media platforms for more expert cleaning content.